Hello, good afternoon, good morning, and welcome to IEA Bioenergy webinar series. My name is Chiara Benetti, and I welcome you on behalf of ETA Florence, technical organizer of this webinar. Today's webinar is entitled Synergies of Renewable Hydrogen and Bio-based Value Chains Deployment, Environmental Performance and Promising Value Chains. The webinar will be moderated by Martin Junginger, Professor of Biobased Economy at Utrecht University and Scientific Director at Copernicus Institute of Sustainable Development. Martin is also VP5 leader of the IEA Bioenergy Inter-task project, Synergies of Green Hydrogen and Bio-based Value Chains Deployment. Today's speakers will be Richard Kingsley Paddy, postdoctoral researcher at Copernicus Institute of Sustainable Development, Utrecht University, Andres Martinez Arce, researcher at the School of Biological and Chemical Sciences, Ryan Institute, University of Galway, and Christiane Hennig, senior research associate at DBFZ and lead of IEA Bioenergy Inter-task project, Synergies of Green Hydrogen Bio-based Value Chains Deployment, and also lead of IEA Bioenergy Task 40. As usual, you have the possibility during this webinar to drop questions by using the Q&A tab that you have at the bottom of your screen. You can use it throughout the duration of the webinar, and our speakers will have the possibility to reply to your questions either by typing the reply directly in the tab or by replying live at the end of all presentations during the Q&A sessions. Please do not use the chat for questions, but only the Q&A tab. I remind you also that this webinar is recorded and that the recording and the presentations of the webinar will be available in the next few days on IEA Bioenergy webinar website. Sorry. So that's all from my side. I'll give the floor to Martin and enjoy the webinar. Thank you.
Thank you very much, Chiara, and also from my side, a very warm welcome to this webinar series and to these three speakers. I think Chiara already explained the technicalities quite nicely. I would encourage everybody to ask questions already during the presentations. We will have the Q&A session at the very end, so we will not stop for questions in between. However, once the speaker is finished, they will already be able to answer small questions, for example, on clarification, etc., right after the presentation. And then we want to focus the Q&A session mainly on the content, on an overarching discussion about the use of hydrogen and biofuels, which this webinar and this project has already been about. So it's once more my pleasure to introduce Christiane Hennig. Christiane has been leading this project for the last 3 years with a lot of energy, and I know nobody who is better in place to actually provide an overall overview and introduction to this webinar today. So Christiane, over to you.
Thank you, Martin. I'm just sharing my screen. So I hope my screen is visible.
Yes.
Excellent.
But not in presentation mode yet.
It's getting there. So
now it is.
Perfect. Thanks, Martin, and also for the introduction. So as mentioned by Martin, first, we kind of would like to start with a little intro, just to kind of setting the scene also for the two presenters to come. So the background and idea of my presentation is now to give you an idea on the topics that we have been looking into in terms of biomass-based hydrogen, but also renewable hydrogen uptake into bio-based processes, and which was leading then also to this webinar and also the presentations to come. So for this, I would like to walk you through to a little introduction, so to give you some background on our motivation. So within IEA Bioenergy, we started looking into renewable hydrogen activities, of course, many years back, but kind of 4 years, 5 years back, we kind of found the motivation to say, okay, we see that there is a need to provide information and data on biohydrogen, and also how renewable hydrogen could act within bio-based processes or value chains, as we kind of saw that this is an overlooked topic and an overlooked activity, and there's not much around yet, also in comparison looking into power-based hydrogen. So kind of the floor on renewable hydrogen is mainly with power-based hydrogen. So this was kind of the motivation to give more info on this area. And here we kind of decided to have like two core areas. One was to really look into technologies and concepts that are out there to realize this. And on the other hand, to really look more on the assessment and into the system perspective. So to how to understand how this could support energy systems or the general way to net zero, but also to understand, of course, with this, the environmental performance. So if we would produce hydrogen from biomass, what would this mean? And also to understand the climate effects. And this is kind of the core of this webinar today. So this brought us then to set up an Inter-task project. So what does it mean, Inter-task project? This implies that within IEA Bioenergy, different topics are governed as part of tasks. These tasks, they look into different aspects and angles of bioenergy or bio-based value chain activities. And here we have like at the moment 9 tasks that are kind of contributing with their knowledge and expertise to this topic of hydrogen and bio-based value chains. And the overall project is coordinated by IEA Task 44, which is on flexible bioenergy and system integration. And today we mainly have representatives here from Task 45, Task 44, and Task 40 who are organizing this webinar. So why was this important? It is important. So why did we decide to have this as a core topic? As mentioned to you before, we kind of saw that it is an overlooked area, and we would like to shed some light on this. And here you kind of see summarizing facts on both producing biohydrogen, but also using renewable hydrogen in pathways. So next to having additional provision of hydrogen or renewable hydrogen, also looking into these value chains that are based on biomass for hydrogen, you can see also additional products could be supplied, as also listed here, for example, biochar, biomethane. You can also support and add additional to negative CO2 emissions. So this would get also an extra added value, which is not with renewable hydrogen based on power-based hydrogen. So this is some additional facts that we saw from this angle. And also when looking into renewable hydrogen uptake into bio-based value chains, you also see here, you can have benefits in terms of either replacing conventional hydrogen, so this is mainly fossil uses. You could then, on the other hand, also improve the quality of an existing product. So you could have, for example, a boosting of within biomethane. So this would result in a better product at the end. Or you could even produce additional products that were not there before, but are on a bio-based origin. So I think this is something that is really worthwhile to consider, and also for you to understand. So looking at these 3 last bullet points, the complexity, of course, increases. So replacing would be an activity that requires less intensity and changing concepts. But of course, producing and altering processes is more of an advanced activity. So in this IEA Bioenergy project, we already had previous activities. So as Martin mentioned, we are kind of running this activity for 3 years now. And here it's just listed for you some further information. So we had a first webinar leading to this webinar. And in this webinar, we were kind of presenting this one part of the project, the different technologies and concepts. Here's also added for you, if you're interested, the link to the different presentations and also to the webinar recording from back then. So also something that you can look into there. And today we're having the second webinar, and here is the focus on the environmental performance and the climate effects. And kind of to get the first idea on promising value chains, since we now have an idea on the technologies and the concepts out there. And now we also have a first idea on some of the cases and their environmental performance. This will then also lead in combining these two efforts in an overall workshop, which is also kind of already planned. So what you can see is here is already taking place on May 15th. It is a in-person workshop, but of course online participation with some limited access to the discussion is possible as well. It's organized jointly with the Hydrogen TCP and IEA Paris at IEA Paris premises. And also here you can see the link to the registration. So who is interested following this webinar, following our Inter-task project activities, is of course welcome to join either in person or online this workshop. And there we will really put the essence together from both of our streams within the ITP Synergies of green hydrogen and bio-based value chains deployment, but also have a discussion with the IEA Hydrogen TCP, which also, next to having a larger look at the different colors of hydrogen provision and having a strong background, of course, with renewable hydrogen from power-based resources, also has a background and information on biomass based hydrogen. So this kind of something to bring this together, and we will have there really overall discussion to provide a picture of this general setting of bio-based hydrogen and renewable hydrogen. As today's webinar, as mentioned today, we really want to dive into the environmental performance. Here we will hear some selected life cycle assessment study results and their related climate effects that have been identified, and thereby reflecting, of course, also on the role on the power-based hydrogen, how this would be regarded in respect to providing hydrogen from this area. And then, of course, resulting in the first synthesis of promising value chains that we identified, or that we see kind of the benefits and opportunities, but of course also the challenges if we would provide hydrogen from biomass or use renewable hydrogen. So then let's dive into this more deeply. So I have two more slides, and these slides are seen as a real introduction to our next presenters. So the first slide gives an overview on the case studies on hydrogen from biomass that we kind of identified within this project, and we kind of went deeper into. And there was kind of the idea to have a coverage from different areas in the world, but also trying to have a coverage of different technologies when possible. And here we really were trying to shed light on which technologies are already there, which technology readiness level are they at, and where do we see kind of a development. And for this, we also had the support of different project developers that you can see on your left-hand side. So these companies or project developers kindly also provided us with some inputs, participated in workshops, and provided data and information to some of our activities. So this brought us to kind of look closer into the highlighted cases, which you can see here. So in the next presentation, you will hear some more information, especially on those in terms of the environmental performance. And here it's a real disclaimer that we also want to do, and also the next presenters will highlight again, is that we took information from these actual projects, from the exchanges and the discussions, as one of the inputs, and we're combining it with general assumptions, and then to produce generic results on climate effect. So these will be provide a more generic picture. And also for you as an information, there will be further reports published soon. When you always see here already the names like Lundgren, you can also later on download these reports, so you get this detailed information on the cases itself. So the next slide is the same. Then for the uptake, these were the different uptake concepts that we found interesting, and we're looking into more deeply. Also here, the idea was different global coverage. So to have like more different areas where these concepts are at, having different different technologies, but especially here also to have like a good mix of different products and byproducts. I think this kind of enriches also this idea of having these different levels that you saw before to replace fossil hydrogen, but also to improve our products that we're producing in bio-based value chains. And here highlighting that with regard to the technology, we were mainly here looking into the HTL concept and to have an additional, also different technology next to the other one, like gasification and pyrolysis that you will hear later on. So this would be for now the introduction slides for this webinar. And I will also now stop sharing my screen. And as Martin mentioned, if there's already some question or clarification, then happy to receive them.
Thank you, Christiane, for this comprehensive introduction. And indeed, I would like to point out once more for those who have joined late, if you have any questions for Christiane, please put them in the Q&A box, so not in the chat, but in the Q&A. I can already see a couple of questions, 3 of them there. And I'm thrilled to say that we have more than 300 participants, so I'm anticipating many more. I'm sure Christiane will already try to answer a few of them, and we will also keep some for the Q&A, which will be at the very end of the session. It is now my pleasure to introduce my colleague, Richard Kingsley-Paddy. Richard holds a PhD in chemical engineering from Stellenbosch University. He's currently a postdoc researcher at Utrecht University, focused on sustainable energy systems, life cycle assessment, and biorefinery design. His interdisciplinary work integrates engineering, sustainability, and clean technology insights to contribute to solutions that advance a more sustainable future. And Richard has also worked very hard in the past year or so to synthesize a number of individual studies to compare them and show us the overall benefits of producing methanol, biocrude, and biogenic hydrogen from biomass and electrolytic hydrogen. Richard, the floor is yours.
Yeah, thanks, Martin. Yes, can you see my screen?
Yes, perfect.
Okay. All right, I guess we can get into it now. So thanks again, Martin, for that nice introduction. And thanks, Christine, for the presentation on the promising concepts of bioenergy and hydrogen synergies. Now, building on that, I will be sharing insights into the environmental impact of integrating wood chip-based value chains and green hydrogen systems. I must also add that this work was actually a result of a collaboration between a research team at the Copernicus Institute of Sustainable Development at Utrecht University and colleagues from KTH Royal Institute of Technology, as well as Aalborg University. So I'm only the mouthpiece here. All right, so by way of introduction, this presentation focuses on 3 main product systems, which were selected for their proven technologies, their common use of wood chip feedstock, and then standardized outputs. So first, we examined a process simulation-based advanced biocrude fuel system. And here, 2 routes were considered. One involving biocrude conversion with electrolytic hydrogen uptake, and the other combining biocrude with synthetic methanol, again, synergized with electrolytic hydrogen. Second, we looked at biomethanol systems using 2-stage gasification technology that's developed by Torgas, as mentioned earlier by Christine. And here too, 2 routes were explored for the gasification technology, including the 2-stage gasification pathway, but in a standalone configuration, as well as its integration with electrolytic hydrogen. And these 2 were then compared with a third scenario where we have simulation-based synthetic methanol using electrolytic hydrogen, also via a hydrothermal liquefaction pathway. And our third process value chain was the biohydrogen. Here also we looked at 2 process routes, one using Cortus AB company's pyrolysis gasification technology, and the other using Torgas's 2-stage gasification system. And both technologies were benchmarked against the electrolytic hydrogen from proton exchange membrane electrolyzer, henceforth will be referred to as PEM in the presentation. So our study was mainly aimed at addressing three main research questions regarding the comparative environmental performances of these product value chains that we've identified. The first is the fact that we wanted to understand which biofuel systems or process level synergies most effectively enhance the sustainable production of biofuels and the biohydrogen. Next, we also aim to answer the question on how do the biofuels compare to fossil or conventional alternatives. And here we are mainly looking at a comparison of the biocrude versus fossil diesel, the biomethanol versus natural gas-based methanol through the steam methane reforming pathway, and also the biohydrogen compared with natural gas hydrogen, as well as the PEM electrolytic hydrogen. And the last question we sought to answer was, how do the biofuel systems perform under different geographical electricity mix scenarios? But here our main interest lies in the impact of the carbon profiles of the grid mix on the climate performances of these biofuel systems. So to our research approach, our main research approach involved conventional life cycle assessments, which was in line with the ISO standards. And here specifically, we were looking at a consequential life cycle assessment, which was focused on a cradle to gate scope. The geographical scope was also limited to Western Europe, and we set the temporal scope to the year 2030. So we are really interested in a perspective into the year 2030. And we also specified our functional units as producing of 1 gigajoule fuel. So in other words, we are comparing all these technologies on the basis of they producing 1 gigajoule fuel. Next, we gathered primary life cycle inventory data as well as infrastructure projections from related pilot plants and process simulations. And these were then supplemented with background data from EcoInvent. For the environmental assessments, we applied the recipe 2016 midpoint method with a focus on three key impact categories. One being the global warming potential, the terrestrial acidification, and the freshwater eutrophication impact. I must also add that these three were selected to represent emission impacts to air, land, and water bodies. So it sort of gives us a fair representation of the overall impacts. But in the entire presentation, I will focus more on the climate impacts or the global warming potentials in the interest of time, and touch a bit on the freshwater eutrophication, the terrestrial acidification impacts. Now let's take a look at the process descriptions for the three product value chains, starting with the advanced biocrude fuel systems. The route 1 adopts a hydrothermal liquefaction and hydrotreating of wood technology, which is synergized with electrolytic hydrogen. And in the process, the excess hydrogen is recovered using a pressure swing adsorption technology and membrane separation technology. And this is also followed by heat recovery from the discharge gas streams. The route 2 builds on the The route 2 builds on the route 1 by incorporating a carbon capture and utilization system, which is also aimed at methanol production. So here we are looking at incorporating synthetic methanol production into the biocrude process. Next is the biomethanol value chain, where three production routes were explored. Route 1 uses the two-stage gasification technology, that's the technology of gas, where the hydrogen in the resulting syngas is actually adjusted using a water gas shift reactor. And this is mainly to meet the stoichiometric requirements for methanol synthesis. Now in our biomethanol route 2, which is similar to the route 1, we incorporate electrolytic hydrogen to supplement the syngas hydrogen for higher biomethanol yields. And in the route 3, we were looking at a synthetic methanol process using the hydrothermal liquefaction technology. And in this route, the electrolytic hydrogen is actually used in both the hydrotreating and the methanol synthesis step. So here we've expanded the scope of the electrolytic hydrogen application. Now to our third product system, which is the biohydrogen. Here also we explored two technology routes. The first one employs the Woodrow technology developed by Curtis AB Company, which combines pyrolysis and gasification unit operations. And the route 2 was based on the two-stage gasification technology, which is developed by Torgas. Their downstream is somewhat similar because they are both using pressure swing absorption for the hydrogen recovery, as well as water gas shift reactions to enhance or enrich the hydrogen content of the streams. Now to some key assumptions in the modeling. First is the fact that in modeling the feedstock supply chain, we assume that the wood chips will come from forest residues and they will be transported by diesel-powered trucks. We also considered a substitution approach to account for the co-products in the multi-product system. So for instance, the biochar byproduct was assumed to replace pulverized coal in steelmaking. And I must also add that we also credited the biogenic carbons in the biofuels using the conventional -1+1 approach. And this approach sort of recognizes the difference in combustion CO2 emissions compared to the fossil fuels. So for the 2030 electricity mix in Western Europe, we modeled a fairly clean marginal mix with over 90% of the contributions coming from renewable sources. In addition, we also conducted a sensitivity analysis to explore how the different geographical grid mixes could actually impact on the environmental performances. And here we were looking at specifically the marginal mixes of USA, Brazil, India, China, and South Africa. Now to our key findings, starting with the biocrude process routes. And again, I'll focus more specifically on the results related to the global warming potential or the climate impact category. So for route 1, which involves biocrude production with electrolytic hydrogen uptake, the main contributors was the hydrothermal liquefaction and the hydrotreating steps. And their impact mainly originated from their catalyst use as well as the natural gas-based heating. And this was followed closely by the PEM electrolysis operation for the electrolytic hydrogen production, which actually accounted for about 41% of the impact. Turning to the route 2, where synthetic methanol was actually integrated into the biocrude system, the PEM electrolysis actually stood out as the dominant contributor to the climate impact. Again, this is largely driven by the high electricity demand and the nature of the grid mix that we considered in our study. However, compare both biocrude systems to conventional fossil diesel, we observe a clear potential for climate impact reduction. And in summary, the key environmental concerns of these biocrude processes are actually concentrated in their operational phase, mainly influenced by their catalyst use and the thermal energy and electricity mixes that we considered in these models. Now let's turn to the biomethanol scenario. In the route 1, which focuses on gasification-based biomethanol, the main climate impact comes from the feedstock stage. And this was mainly due to the electricity used in the biomass torrefaction operation. When we look at the route 2, where electrolytic hydrogen is actually integrated into the gasification process, the methanol production process actually was identified as the main contributor to the emissions. Again, this is mainly driven by the electricity demand and the mix of this methanol production facility. In the route 3, which is the synthetic methanol pathway using electrolytic hydrogen, the methanol production facility again was the dominant actor in terms of the climate impact. However, the credits from the biocrude byproducts that we modeled significantly help in reducing the overall impact of this scenario. We can therefore conclude that while the integration of gasification and electrolytic hydrogen can actually boost the biomethanol use of this biomethanol gasification processes, there is a trade-off, which is actually a higher environmental burden due to the high electricity demand and mix of this PEM electrolysis operation. But in conclusion, provided that we are actually powering these biomethanol production systems with a greener electricity, we anticipate that the climate impact of this biomethanol processing would actually be always less than half that of the natural gas-based methanol scenarios that we are currently using. So that's an advantage of the biomethanol scenarios when it comes to the climate impact. Now to the biohydrogen systems. We observed that the feedstock related impact was quite higher in the two-stage gasification route when compared to the pyrolysis gasification route. And this was mainly due to the electricity demand in the additional torrefaction step in the two-stage gasification process. So there wasn't any torrefaction step in the pyrolysis gasification as compared to the two-stage gasification. That accounted for this high feedstock impact. However, if we take a look at the overall climate performance, the byproduct biochar credit actually emerges as a major differentiating factor. In the pyrolysis gasification hydrogen process, we actually recover the biochar from after the gasification process. But in the two-stage gasification, the biochar was recovered from the low temperature phase of the gasification process. So that yielded a higher amount of biochar compared to the pyrolysis, which also translated to a higher environmental benefit. And overall, when we compare the biohydrogen pathways with the PEM electrolytic hydrogen, we can actually see that they outperform the electrolytic hydrogen option. But then the electricity mix is the key determinant here because it drives over 97% of the electrolytic hydrogen's impact. In other words, if we have a fairly cleaner electricity mix, then we're anticipating that the PEM would perform better. But for a fairly or a relatively dirtier electricity mix, you may be seeing the biohydrogens overtaking the PEM option. Now to our geographical marginal grid mix impact on the climate performances. The sensitivity analysis that we did on the geographical carbon grid profiles actually showed that the turnaround emission factors, that's the emission factors where the biofuels no longer outperform the fossil alternatives, would range between 0.08 to 0.04 kilograms CO2 equivalent per megajoule. And when we compare these values to the regional grid emission factors, which also ranged between 0.03 to 0.11, we see that the emission factors for all the regions fall below these critical thresholds for the performance turnaround, with the exception of the biocrude plus synthetic methanol route 2 process, whose turnaround factor actually stood at 0.08 kilograms CO2 equivalent per megajoule electricity. But what this findings tells us is that the biofuel systems actually are quite resilient in maintaining lower emissions than the fossil fuels. Even if we look at it across the different regional electricity mix scenarios, they are going to perform fairly stable in terms of lowering the emission impacts. And now to the comparative performance of all the alternative routes that we looked at. In the performance comparison, the 7 process routes were actually ranked from 1 to 7, with 1 being the best and 7 being the worst. And if we take a look at the results, it's actually clear that there are performance trade-offs between the various biofuel systems. So for instance, when we take the gasification biomethanol, it comes out ahead in terms of the global warming and freshwater eutrophication impacts, while the synthetic methanol route performs better in the terrestrial acidification category. So if we look at the context of our study, and assuming we have limited biomass wood chip supplies, then the most promising biofuel pathways will be the standalone gasification biomethanol and the gasification biohydrogen systems, which do not actually rely on the electrolytic hydrogen. Now to some overall remarks of the study. The first is the fact that the integration of synthetic methanol production into the biocrude pathway actually has a negative effect on the environmental performance. And we also see a similar trend when trying to boost biomethanol use by adding PEM electrolytic hydrogen. But the drop in the environmental performance is largely tied to the high electricity use and mix in powering the PEM electrolyzers. Also, it is worth noting that all the biofuel systems actually outperform their fossil counterparts when it comes to the global warming impact category. But in the other impact categories, the results are somewhat mixed. And here, factors like the electricity mix and the electrification of biomass transport can actually substantially influence the overall outcomes. So in a nutshell, while the idea of integrating electrolytic hydrogen with biofuel production seems to be appealing, especially in terms of the product yield enhancement and product diversification. It would only work well if we are also using low impact renewable electricity in the operations. Thank you.
Thank you very much, Richard. And I can already see a wealth of questions in the Q&A. So I think Richard deserves a well-deserved breather, and then we'll try to answer a couple of them in the chat already. And that gives me the opportunity to hand over to our third and final speaker of today, Andres Martinez Arce. Andres is a PhD student at the University of Galway, Ireland. His work focuses on assessing the environmental performance of anaerobic digestion as part of novel biorefinery configurations. Before starting his PhD, Andres conducted research on advanced processes for anaerobic waste valorization and performed for over 7 years as an LCA analyst for the public and private sectors internationally. And I think this experience came in very, very handy when he carried out the next 2 case studies he's going to present in a second. Andres, over to you.
Thank you very much, Martin. So I'm going to share my screen to start this presentation. Second. That's it. So can you confirm that you can see the screen, please?
Perfect.
Okay.
In presentation mode. All good.
Thank you very much, Martin. So I'm going to talk to you about 2 case studies in this presentation about I'm going to start with the goal and scope definition for these 2 case studies, and then I'm going to dive into each of them separately. So in this case, we wanted to understand the environmental impacts of biogenic hydrogen production through novel value chains involving anaerobic digestion. So in this case, we also used as a functional unit the production of 1 gigajoule of hydrogen. And these are the 2 value chains under analysis in this case. So there was the first value chain involving a 2-step anaerobic digestion. 2-step meaning dark hydrogen production, dark fermentation for hydrogen production, and then methanogenic reactor. And then in a combination with electrolysis to get more hydrogen and use the residual heat in the process. And in this case, the feedstock would be industrial wastewater, and that comes from a pilot scale process with a technology readiness level between 4 and 5. So that means it's in a demonstration scale, in a scale from 1 to 9. And the developer in this case, the Research Institute of Sweden. And the second value chain I'm going to talk about is the combination of anaerobic digestion and biomethane pyrolysis. And in this case, the feedstock is bio-waste and solid bio-waste. So in this case, we have also data from pilot scale, but this pilot scale is more from an industrial scale more than a demonstration scale. So in this case, we got data directly from the developers and also the University of Oulu. So we are working in a publication involving these value chains, but also their value chains will be involved in that publication for my PhD. So what was the process we used for data analysis? We followed ISO 1444. This would be like just an adaptation of what ISO established. We started with the data collection process, collecting data for mass and energy balances from the data providers. In the case of the 2-step anaerobic digestion and electrolysis, we got data from the Research Institute in Sweden, biomethane pyrolysis from the University of Oulu, and the anaerobic digestion of the solid bio-waste is from a model that I have been enhancing that was developed in our research group to describe the anaerobic digestion of this kind of waste. And after that, we conducted the data validation just to be sure that all the mass and energy balances were correct, and also that the values were similar or in similar ranges as compared to other processes, similar processes in the literature. After that, we worked relating the data to functional unit. And in this case, the life cycle analysis consider a cradle to gate scope. And in this case, we used an attributional approach with expanded boundaries to account for the co-product or to manage co-products and with a product substitution methodology. And we are using as a baseline, the electricity mix is the European average, but then we conducted sensitivity to understand what was the difference in the impact if we changed the type of energy that will be used in the system. Well, at the end, we aggregated the data and we used EcoInvent to represent all the background data in our system. And also we used CIMAPRO to model this, and we used the impact assessment method recipe midpoint 2016. So we're gonna see the details about the first value chain. So as I mentioned, in this case, we have a wastewater treatment for wastewater coming from a sugar industry. So in this case, it's a two-step anaerobic process. It consists of a fermentation reactor, but in order to inhibit all the methanogenic bacteria, it's necessary a pre-treatment, a heat shock at 90 degrees. And then after that, we get a biogas. It's not possible to completely inhibit the methanogenic bacteria, so there is still a little bit of methane there in the biogas. And after that, we have the effluent goes to a methanogenic reactor in which we get biogas consisting of methane and carbon dioxide. And then afterwards, we conduct a separation of CO2. And in the baseline scenario, we assume that this carbon dioxide is emitted to air, like it's vented. But in a scenario, we also consider that we can capture it and use it as a substitute for liquid CO2. And then there is another separation of to get like the specific product we are evaluating. This is the hydrogen. And then we get also methane that could substitute natural gas in our systems. And then in this first configuration, the effluent goes to conventional treatment to polish, and after we can finish this process. But then the second configuration includes an electrolyzer. So in this case, the idea is to use the effluent coming from the process or from the system, and to apply an advanced with water purification process, and then use this water as an input to an alkaline electrolyzer to get more hydrogen. And then there is a waste heat that can be used in a heat pump and recirculated back into the system. And this will avoid the use of external heat for the pretreatment of the process. And then some heat, excess heat could be used and can potentially avoid the production of heat in other systems. So this is the two configuration of this first value chain. And here what I'm showing you is the results, the contribution analysis for the 18 impact categories in the recipe midpoint methodology. So what we are seeing here is we have like normalizing 100% the contribution of every one of the processes or elements of the inventory to the environmental impact. So we must analyze separately each one of them, but we have insight of what are the most important elements across all the categories. So what we can see there is that there is blue, a lot of blue we can see here in this figure. And this is because of the electricity. The electricity in this case is the dominant element for the environmental impact. And it's important to remember that in the baseline, we are considering an average mix containing still a little bit of fossil energy. So the other thing is heat consumption. We can see here that there is a little bit of orange that we can spot across the different categories. And also in the climate change or global warming category, you can see that fugitive emissions coming from the methanogenic reactor are relevant for the environmental impact in this category. And then for other categories, for example, in marine eutrophication, we see that the treatment of the effluent is relevant. So this is the contribution analysis for the first configuration. And what happens if we include an electrolyzer? So in this case, we have almost the same performance with a few differences. For example, there is no heat consumption because of we are recycling the waste heat, and then we are avoiding the use of this external heat. So we don't have orange now. And we start to see some gray areas, and these gray areas correspond to infrastructure to build the electrolyzers. So we see that the infrastructure starts to play a significant role in the environmental impact when we include an electrolyzer. So this is the contribution analysis, and we saw it relatively in 100%, but what happens in an absolute terms, like absolute values? And I am showing you here now the absolute values for this like baseline scenario with the average electricity mix. So what we see here is that in this case, including an electrolyzer would increase the environmental impact. We can see that this is because of the impact coming from the electricity, because of the high electricity consumption, and also because of the need for materials to build the infrastructure. What else we can see here? So in the two-step anaerobic digestion system, we see that there is a lower use of abiotic resources. But in this case, the fossil reference generating hydrogen from steam methane reforming is still behaving better. But then, also this is the impact from the treatment of the effluent. But then what happens if we use, instead of average electricity mix, we use wind electricity, and if we use the carbon capture during this process of purifying the final product. So what we see here is that we have more green here in the two-step AD, and this is thanks to the lower impacts coming from renewable electricity, and also avoided burdens coming from displacing liquid carbon dioxide in other systems. So, however, there is still an important environmental impact coming from the treatment of the effluent. So we have trade-offs still in this case. And also we can see that when we use an electrolyzer, even though we are able to reduce the impact of the product, there are still high impacts coming from the infrastructure. So in this case, the conclusions are that the most relevant life cycle inventory elements in this case are the electricity consumption, the infrastructure in the case of when the electrolyzer is included. Also, if we can use the carbon capture during the product purification, it will be very useful. And also the treatment of the effluent and some fugitive emissions coming from the methanogenic reactor are important depending on the impact category we are evaluating. So under the baseline scenario, using European electricity mix, the fossil hydrogen outperforms this value chain, except for fossil resources scarcity. However, under a best case scenario, using wind electricity and carbon capture use, the process is a best alternative. It's a better alternative in almost all impact categories, although we still have some trade-offs. And including an electrolyzer would increase the electricity consumption and also decrease the production of biomethane and carbon dioxide. So this would in overall increase the system environmental impact. Sorry. So these were the conclusions for the first case, and the second value chain is biomethane pyrolysis. So for this value chain, I am presenting here the system boundary, and we can see that we are using a feedstock. It could be cattle manure or food waste. It depends on the scenario. And this goes to anaerobic digestion. And then in anaerobic digestion, we get biogas, and this biogas goes to upgrading and digestate. And the digestate can be used to displace fertilizers, mineral fertilizers. So the biogas goes to this process of upgrading, and here we get also biogenic CO2 that in a scenario it can replace liquid CO2. However, in the baseline scenario, we assume that this CO2 is emitted to the air. Then the biomethane, the purified, will go to pyrolysis, and in this case we get high purity carbon as a product and as a co-product, and this will replace, in this case, in the baseline scenario, we assume it displaces carbon black because of its high purity, and then we get the final product, the hydrogen. So this is the contribution analysis for this value chain. And as we can see here, we have a relevant contribution from an anaerobic digestion system. And this is the dark blue with the dots, with white dots. And we can see that depending on the impact category, there will be a relevant contribution. However, the production of digestate can be very useful to get avoided emissions or avoided impacts because of the potential fertilizer substitution we can see here in this light blue. Then also the fact that we are generating a carbon product that could displace a high purity carbon in the market implies environmental savings. Then we also have, we can see here that the consumption of electricity is also relevant in this case. And well, I am presenting here the results, the absolute results for the pyrolysis of biomethane. But here I am presenting the results when the biomethane is produced from manure or when the biomethane is produced from food waste. So depending on the feedstock, we will have a different environmental performance. As we can see here, and this is because of the different yields and also different nutrient content in each type of feedstock that would define the environmental performance. So, but we can see that for global warming, both will have a lower impact than fossil hydrogen production. Also, we can see that the fact that we are substituting fertilizer and carbon black helps in reducing the environmental impact compared to the fossil hydrogen. However, there are still trade-offs in this case because in the case of manure, when anaerobic digestion uses manure as a feedstock, this substrate has a high nitrogen content, and this implies high emissions of nitrous oxide and ammonia. So there are some impact categories with high that are higher than for the fossil hydrogen. And for example, in the case of food waste, it is necessary to use water to dilute the waste before entering the AD. And we can see that effect here in the water consumption category. And then we conducted sensitivity analysis for this case, and I am presenting here the result for the biomethane when it is produced by a manure 80. And what we are seeing here is that we evaluated the use of wind electricity and the use of carbon capture and use during the anaerobic digestion system. And we can see that when we combine these two processes, we like are able to get the best case scenario, so to speak, because we are using a low impact energy, and also because of the substitution of liquid CO2 in our systems. Also, we found that when we, instead of substituting black carbon, we use that carbon coming from the process to substitute other lower value carbon, for example, hard coal, we get trade-offs. Like, for example, there is reduction in some impact categories, but there is an increase in other impact categories. So this means it is really important what will happen to this carbon, to the environmental performance of the system. And also, if we incinerate the digestate instead of using it to replace fertilizers, the environmental impact overall will increase. So that's what we found. And the conclusions in this case is that the environmental performance is heavily influenced by the type of feedstock used in anaerobic digestion. So because that defines the methane potential or the nutrient contents of the feedstock. What will happen with the digestate also, because there can be a potential environmental savings if we use the digestate to replace the fertilizers, and also the type of energy consumed. In this case, if it is renewable, it will improve the environmental performance. And also, what will happen with the carbon that is produced during this type of process. So overall, the biomethane pyrolysis has a better environmental performance than the fossil alternative. However, there are some trade-offs. In a worst-case scenario, in which electricity with a little bit of fossil energy is still used, and for example, the digestate is incinerated, this value chain will have a higher environmental impact than the conventional alternative, except for the fossil scarcity potential. So those are the conclusions for this second value chain. And I thank you very much for your attention.
Thank you, Andres, for this very comprehensive presentation of your two case studies. So before we go into the Q&A session, I would like to recap a few things which were already mentioned before, just to explain them once more. I can imagine this was a large amount of information. So for your information, it will be shared on the IEA Bioenergy website. So you will be able to watch back both the webinar and the individual PDFs of the PowerPoints so that you can look at them in your own time again, because I can imagine it was really a lot of information to process within the hour. A few other clarifications once more. So the case studies that were presented are largely hypothetical. None of the technologies that were presented by the speakers today are actually commercially available right now. In a few cases, there are pilot plants available, but there's no commercial operation. And we would like to re-emphasize again that none of the results shown today should be seen as the performance of a particular company. We have collaborated, and we're very happy for this collaboration with various companies to provide input, but we have strongly modified the assumptions. For example, we have assumed a common feedstock, for example, wood chips in the case of Richard, which may not be the actual feedstock that the actual pilot plants use. And we've also taken a lot of other different assumptions to make those case studies comparable. So please do not mistake the results shown now with actual performance from pilot or even lab scale equipment. There was also a few, actually our speakers have been very, very efficient in answering questions online in the text box, but I would like to go on through a number of them just to recap on this as well. One of the questions was, for example, whether land use was considered as an impact category. We can say that actually both in the case of Richard and Andres already showed it, we actually assessed a large variety of impact categories, and we only showed a limited amount of information as you can only process so much in 1 hour. But land use in general, I would dare to say, played a relatively minor role in our assessment because we only used residues, so sewage sludge or wood chips from forest residues, etc. We did not consider any dedicated crops. Another question was how we modeled yields, for example, for hydrogen or CO2. basically all the studies we received either mass and energy balances from the companies, or we did some process modeling ourselves. So that was basically the basis for all the LCA work. I also would like to emphasize that this work all will be published. There's a number of underlying studies, partly based also on master theses, which are already available. But Richard just submitted his work, and I think Andres is also about to as part of his PhD. So this will also be published in scientific articles, and we will be happy to share the final articles when they're published. But right now they are under publication or under review. If you would like to have more details, please feel free to drop a line to Andres and Richard, especially with regard to the input data, etc. We can probably share a lot, much more than was shown you in the presentations, but please contact the authors individually. I think those were a number of general points. I'm briefly running through the questions. I think Christiane already covered everything there was to do in her introductory presentation. Richard, is there anything you would like to highlight based on the questions you have received so that Andres can actually take a look on the questions he got on his presentation? And you're still muted, Richard. You need to unmute yourself.
Oh, yeah, sorry. I think there were some interesting questions on the impacts coming from the chemicals used in the catalyst production. So, yeah, again, it's good to point out that these chemicals are not renewable chemicals, so to speak. They are not from biological origins, for instance. So they are quite high impact in looking at the fact that they are being produced from fossil-based resources as well. And we have to also take note of the fact that the entire or the overall impact of our processes may not be large in terms of the magnitude. But then we are looking at the contributions coming from each of the major actors in the process. That's why we are seeing some of the chemicals representing a high contribution. But in overall, the overall picture doesn't really look that large for the whole process. It's just unfortunate that they are the ones who are contributing to this little overall impact. Yeah. I think that's one of the things to highlight. Okay, there was one for Andres. I think I can skip that.
There was also a question I think we can answer quickly on the biohydrogen routes, whether we considered hydrogen emissions as a greenhouse gas and whether we considered an emission factor. I think we used the standard emission factors from the CIMA-Pro Ecoinvent database, but yes. I don't dare to say so. I'm handing over to you. Do you know if there was any emission factor to any fugitive hydrogen emissions?
We did consider that in the emissions, yes, but we use the database in Ecoinvent, so I'm sure we have to double check that. Yeah.
Very good. And then I see a number of questions which Andres are basically to answer. Andres, are you kind of recovered a little bit from your presentation and are ready to take a few?
Yes.
Yes, sure. I have one unanswered question from Jorge about the emissions related to digestive distribution and NOx emissions on the soils.
Yes. So, well, in this case, I presented the results from a cradle to gate approach. So we are not considering emissions during the application of the digestate. However, we also evaluated the full cradle to grave approach, and that's what we are working now for the publication. So, but it is really important because we have found that those emissions during the application of the digestate are pretty relevant to several environmental impacts. And also, not only that, but also potential counterfactual uses of waste. In the case of, for example, manure management, when we avoid the conventional management of manure, we can also have some avoided emissions coming from that practice. So, yeah, so in this case, I didn't want to go into those details because I wanted to focus more on the attributional part, but that's a really important part of the system. Thank you.
Very good. I have two more comments I would like to, or I'm happy to take on myself, and then Andres or Richard or also Christiana, feel free to add. One is from Eric van den Heuvel about guarantees of origin being used for biogas projects rather than grid mix. Eric, under LCA, basically offsetting is not allowed. So while in the real world, you can basically buy green certificates to green your electricity supply, in LCA, we actually use the physical mixes, or we make assumptions about the physical electricity and not about basically certificates that you buy to. And I think also for this kind of assessment, it's really important to take a systems perspective to see how the overall system is performing, rather than saying, okay, we are going to buy certificates, which may be possible under a certain policy in a country, but not under LCA. And the second question I would like to take up myself is also the question from Ulf Neuling. I will read it out. How reasonable is it to produce hydrogen from biomass or to sequester biogenic CO2 when we also need sustainable carbon sources in other areas such as aviation, shipping, or the chemical industry? Would you give the same recommendations if such conflicts of use would be taken into account in a consequential analysis? This is obviously a super relevant question, which is at the very heart of the overall project, and which we cannot answer simply by looking at individual value chains individually, right? So the short answer is it all depends. In our assessment, we have not looked at the total amount of, for example, available sustainable biomass that can be supplied. Neither have we looked at the total demand for, let's say, hydrogen in future worlds. And this would, and to a very large part, determine the answer of your question. So the LCA only gives the answer of a performance of a functional unit under a certain given set of availability of biomass and basically an assumed amount of hydrogen. Obviously, we live in a constrained world, and as such, it will always depend on the specific conditions on whether, for example, clean renewable electricity and or abundant clean sustainable biomass is available, and of course the demand for both advanced fuels for shipping, which we also assessed in our analysis. What would be the preferential route producing biogenic hydrogen or advanced biofuels for chemicals or for shipping? Personally, I would argue that ultimately we are living in a world which is more constrained with regard to biogenic carbon than to the hopefully future abundant availability of renewable electricity. But again, this is currently not even in Europe yet the case that we have a very clean mix, let alone other parts of the world. So it may actually make a lot of sense to go for renewable hydrogen from biomass, at least on the short to medium term, depending on the electricity mix, as I think was shown by both Andres and by Richard.
Yeah,
Andres and
thank you,
Richard, or
Martin.
Christiana, would you like to add to that?
I think that's a really good question, and I really liked that you worked on this and elaborated so comprehensively, Martin, because I think this is really key also for the audience to understand. So this was really the frame that we had to look, or we're looking into, was really the pathways itself. So we did not say, okay, biomass is already involved in different applications or has already other system activities that it's taking care of. So this is not part of the overall scope. So we were really purely showing, okay, if you decide to use biomass to produce hydrogen, this would be the opportunities, these are the benefits, and these are maybe also the challenges. So this was just really to give an overview what is out there and what would it mean and implies. But we did not reflect on, okay, if we would move now the streams into this use, then of course it could be missing somewhere else where biomass could have an important role to be covered, or maybe even more valuable role than providing hydrogen. So this was not part of it, but I just wanted to add, this is something that we also still look into next. So it's not like that it's now concluded everything, but what we would like to do next also in the network of IEA Bioenergy with all the experts, to see the different system components, how they work together. With having the part of hydrogen, but also having BECCS, having all the different roles that bioenergy can contribute to. So thank you for the question also. Happy to hear what Andres and Richard maybe would like to add to this.
Any additions?
I think the seniors have covered everything, so the
Very
juniors will
good.
just recede, yeah.
Then I have one request to both Andres and Richard, and that is to put your email addresses also once more in the general chat. I already saw you put it in the answers of the Q&A, but I think there's many people who would like to contact you following up on these presentations to get more detailed information or perhaps some input data or to discuss some. I can see many very detailed questions and also some somewhat off-topic questions. We may try to answer those after the webinar, but not in plenary, because I don't think they're so relevant for everybody here now online. I'm seeing a few more general questions. Andres, I saw one about from Hang Reo Na about the comparison between the biomethane pyrolysis and steam methane reforming. Would you like to go into a little bit more once more and how these two perform?
Sure. So we use the steam methane reforming as a comparison. In this case, we got data from EcoInvent. The idea was we wanted to understand how comparable was this novel value chain against that conventional fossil hydrogen production. And also I saw a question in the chat asking about the biomethane reforming. So I think, well, we didn't include that part because we didn't have access to data from a stakeholder evaluating or doing that process. However, it would be very interesting to know. I remember there are already some examples in the literature about that. So I would say the value chain we are evaluating is a little bit exploring this new configuration of pyrolysis with a catalyst.
Thank you very much. I would also take one more question from Lav Kumar about how economics of CO2 methanation works. This webinar today is about the environmental impacts, but we had a previous webinar where we also looked at the wider techno-economic setting. So I would recommend all of you who are also interested in how the technical and techno-economic performance of different value chains looks like to look back at the previous webinar and also take a look at the underlying documentation on the IEA Bioenergy website, where you can find much more information about this topic. This also covers the question from Stanley about the assumptions on production cost. I think it goes without saying that it's safe to say that many of these technologies cannot compete directly with fossil alternatives without a significant CO2 tax or so attached to them. At the same time, we also see costs of, for example, renewable hydrogen expected to drop in the future, which will significantly improve the economic basis for these conversion value chains. I'm looking a little bit at the time. We have about 15 minutes left, but I think we covered pretty much the overarching questions for this webinar. So I'm looking also at Christiana, Andres, or Richard, if you have any further general remarks or questions you would like to answer.
Yeah, then I would just take a final remark and also relating to a question which we received in the chat. And as Martin mentioned, I tried to cover everything already by typing into the chat. But I think it's really important for you to know that there was a question on that how is the weighted average calculated on the TRL? So we are well aware of this, and we kind of were expecting this question because it is something that you also would like to understand. So for us, it was just as a background for you important to state not only like the weakest link, because it's sometimes you have a whole process step and there is one part that has a really low TRL, but the rest is maybe really high. So if we say only the weakest link as the overall TRL, it doesn't tell you like everything about the process that maybe if we manage to have this one process step developed, you know, you can advance much further and easier. So that's why we decided to have both the weakest link to understand, okay, that is the weakest link, so you can't go on with this concept. However, there is an average link to get a feeling how much has been developed already in this area. And more information you find then in the publications on this, on the case studies. And as Martin was saying, they are all then published on the IEA Bioenergy website, and they're about to be publications. So then you can read everything, also the sources and the literature behind the ideas of, for example, this TRLs. And you also can read on all the case studies in detail. So you get everything, the process concepts, You get the mass balances, you get everything that you need more in detail, and you can also listen to the webinar number 1 as a recap where the technologies have been introduced. So this is my final remark. Thanks.
Excellent. Thank you, Christiane. And I don't see any more super burning overarching questions in the chat. So then I would like to thank all the speakers and the IEA Bioenergy for hosting and organizing this webinar. But most of all, also the participants. We had at the peak, I think, more than 310 participants in this webinar. So I would also like to thank all of you for your interest and for your questions. If you are interested in seeing the final results, again, we will publish the final report very soon. And if you're interested in the resulting articles, which hopefully will be published in the coming months, please feel free to drop a line to Richard and to Andres as well, so that they can update you as soon as they have been published. With that, thank you all, and see you next time.
Bye.
Bye.